Hi everyone! So after the last video there was some requests for some more examples and pictures of the bits and pieces that Paul and I were talking about in the basics of aerodynamics for Greenpower cars. Now I've put some of that together for you and I'm going to go through it, but before I do there's just a few basics that I want to touch over again. And the first one is, why do we need to look at aerodynamics in the design of a Greenpower car? Well, if we look at a car, there are three main forces that act upon it. The driving force that pulls you forward, the frictional force between the tyre and the road, and the aerodynamic drag force. Now, out of those resistive forces, the aerodynamic drag is 75% of the system. So it's very significant and important to understand it and to optimise it as much as you can if you want the best performance out of your car. Before I go on to explain some of the flow characteristics, I just need to explain what pressure is. Pressure is the force that's applied over the area of an object, and in aerodynamics, that is the force of the air actually pushing against the object itself. We can resolve the pressure into directions, and that's exactly what we do when we talk about lift that acts up, or drag that acts in the opposite direction to the motion. In areas of high pressure, this is where we have quite a lot of air hitting an object, and it's usually where the surface is perpendicular to the airflow. In areas of quite low pressure, that's where you have less air, or in fact you have none at all because it's a separation region. We don't want areas of high pressure or areas of low pressure because they generate drag. So what we try to do is to minimise both of them as much as possible. But they are unavoidable. So let's have a look at a couple of examples. The first one we have here is actually an aircraft. We have areas of high pressure on the nose of the aircraft, on the windows of the aircraft, on the wheels, and also on the engines. This is because all of these are perpendicular to the airflow, and it's the first thing that the air sees when it hits it. The next example is a helicopter. Again, the areas that are perpendicular are the areas that we see high pressure. On the nose of the aircraft and on the top up here. You can start to see the pattern. On the motorcyclist, again, we see the areas of high pressure right at the front on the wheel, on the top of the helmet, and quite a lot in the bay in there. This is an example of a bobsled, exactly the same. Now, bobsleds are designed for low drag, so we can see we've got a very, very small amount right at the front. And this is the sort of thing that we want to do when we start looking at our Greenpower cars. This is an example of the Bloodhound. Now, the Bloodhound has quite a large pressure area at the front, but it goes quite nicely into a green region, and that's quite a neutral pressure region. Areas that are blue, like the top up here, that's probably where we'll see flow separation. And lastly, we've got an example of a Formula 1 car. Again, we see quite large pressure regions on the nose and on the wheels, a little bit on the helmet, and again on the air intake up there. You'll also see quite a lot on the front here, on the front wing, and also on the rear wing. That's for a slightly different reason, because you actually need that pressure to generate lift or downforce. If we have a look back at the aeroplane, and I'll insert it just up here, you can see across the top of the wings that they are blue, and that's where we have a low pressure region. On the underside of the wings, they're in fact orange, and that's because you've got a high pressure region. Lift is generated as a result of the difference between these two pressures. In Formula 1, what we want to do is, instead of generating lift up, we want to generate lift down. So we flip that over. So now we have high pressure regions on the top, low pressure regions on the bottom, and lift force generation acting down. We don't need to worry about that in Greenpower because we don't want to generate lift or downforce. But that's why in that particular image, it's okay that we have quite a lot of red in those two areas. So let's have a look at a Greenpower car. And I've got a couple of examples here. One of kit cars and one of scratch builds. So looking at the first kit car, we can see that we have high pressure regions on the front of the wheel, on the arm between the body and the wheel, on the front of the nose, and then the same on the other side. That's quite a lot of pressure regions there. And what in fact we want to do is to minimise them as much as possible. So if we look at the scratch build on the bottom, you can see that the pressure regions, there's a very, very small amount on the nose and then a very small amount on the helmet. The bottom one would have better aerodynamics because you do want to minimise those pressure regions as much as possible. The other thing we want to do is to make sure that the air around the front is as smooth as possible. So if we have another look at that kit car, you can see here that we go from red to blue really quickly. And that's an indication, the blue is an indication of flow separation, which means that you don't have a very good shape around that front. And in fact, the air, it can't stay attached to it and it just becomes separated. The fact that it goes green afterwards, here, means that you might have a bit of flow reattachment. But the first thing you could do is have a look at trying to smooth some of that nose out. Again, if we look at the Silesian car, the green one at the bottom, you can see that it goes from red through yellow and into green in a nice, smooth way. That's the sort of thing that you need to look for when you look at your CFD results. If we look at the other image of the scratch build, you can see that there's red on the nose, it comes through the yellow and into the green in a nice way, but actually there's quite a region of blue here. And that suggests that that shape probably isn't the best because really you want to keep that area nice and green and as much as you possibly can. But if we have a think about the package, it probably suggests that that's where the wheels are, so it can't be made any smoother or any rounder. If you look back at the Silesian car, the reason that they've been able to be nice and smooth is because their packaging of their wheels is slightly different. So this is why, when Paul and I were discussing before, the package of how you want to design your car is so important. The other thing that we can see on this image here is a high pressure region just before the cockpit area. And that's probably because a little bit of a lip has been applied to direct the air up over the helmet and the head of the driver. That's not necessarily a bad thing. It does mean that a little bit of drag will be created in that area, but it's probably less than what was created if you didn't have that lip in the first place. Now, we also have a few characteristics around the helmet and the roll bar, but I'm not going to touch on those just yet. I'm going to circle back to them. So, the other thing that you need to consider when you're designing your Greenpower car is the wake structure that happens behind the car itself. Now, there's two types of drag. There's skin friction drag, which is the friction between the air and the surface of the object. And there's also form drag. Form drag occurs from the actual shape of the object itself and where separation might occur. And in Greenpower cars, your form drag is going to be your dominant factor. So let's have a little bit of a think of what we think the wake would be of a kit car versus a scratch build. So wakes occur from separation. So if we have a look at this kit car, we're likely to have flow going like this over the top, separating off, maybe some reattachment over the helmet, and separating again about here. I'll discuss helmets in a little bit more detail in a second. Underneath the car, you're probably going to get flow going under, straight along, and then separating at the rear, maybe a little bit like that. So you've ended up with quite a large wake. Let's have a look at the scratch build to the right of it. You're likely to have flow over the top of the car. There's a little bit of a flip directing it to the helmet. Maybe a little bit of separation here, but you have a fairing. Flow going to the rear and then separating off like this. On the underside, you're likely to have flow coming underneath, staying quite nicely attached, and then separating there. You can see now that that wake is much, much smaller, and you want the smaller wake to have less form drag. This is why we look at cam tail designs. If we hypothetically had a point here, instead of air being separated at this point here and going backwards, it could continue to attach to the surface and actually start to accelerate up, which means that your wake, although it's smaller, much smaller, is now unbalanced. And what we mean by unbalanced is it's not symmetrical top to bottom. Instead of sitting in this central region here, it now sits a little bit too high. And that can also induce drag. So what we want is a nice balanced wake. This image here is a good example of a balanced wake. It stretches far enough into the wake that it doesn't interfere with the rear of the car. It's quite small in size and it's quite central to the midpoint of the car. This image is a good example as well to explain the importance of height off the ground. As you can see underneath, we have regions of yellow, and the regions of yellow demonstrate high velocity flow. If the car was too high off the ground, you wouldn't get that accelerated flow, which means that the rear wake wouldn't be pushed up in quite the way that it is, and you could end up with a wake that actually looks a little bit more like this. And you can see it's a bit larger than what we've actually got. By pushing the car lower to the ground, we accelerate that flow and we can make that wake much smaller, hence reducing the drag. And underneath is an image of this actual car that is run by Silesian University of Technology. So one of those problematic areas that I mentioned was the helmet. So let's have a look at the flow characteristics around it. And you can think of a helmet a little bit like a sphere. You have flow coming onto this sphere, travelling around the first half, front half, and then separating around about the midpoint. Now, when you have fast air around the outside of it, up here, this airflow will start to turn and you will end up with vortex shedding occurring off the rear. And that creates really chaotic flow and will in turn induce drag. I'm going to insert a video now trying to show this in 3 dimensions. And don't worry about the colours too much. It just shows the clockwise direction versus the anti-clockwise direction. If you have a lot of this chaotic airflow, then that dirty air is actually hitting the roll bar and you can't really control any more of the airflow past the helmet. In fact, if we look at a CFD image from earlier, you can see that we start getting flow separation off the top here, and that you start getting those circulation regions, as we call them, where the air is starting to rotate. And actually, all of the helmet and the roll bar are in completely dirty flow. One way we can deal with that is to create a fairing from the helmet. And what that does is to promote flow attachment off the helmet and continue it rearwards so we can have really good control of that wake. So now, if we have a look at it, the airflow will hit the front of the helmet, travel round, continue to be attached onto that fairing and down into the wake. That's why you see quite a lot of these fairings on these scratch build cars. Now, depending on how close the head of your driver is to your roll bar, you may or may not need this central region. And we can see the benefit of this fairing in CFD. So if we have a look at this image on the right, and now we're looking at flow velocity, you can see we've got the stagnation point, the point at which the air hits the helmet at the front here. It continues to be attached. There's a little bit of separation in this region here, and you can see a vortex being generated there. But it continues to be attached over the fairing and down into the wake. You can also see a little bit of separation off the rear of the roll bar here, and you can see a little bit of vortex generation there, and you can see that there's also separation off the roll bar there, and again you'd expect to see vortex generation there in the blue region. So another one of the problematic areas and one of the big debates is wheels inside or outside, and this really depends on your design and, as Paul and I have mentioned, your package. An example here that we have from Sandbach High School actually have wheels in and wheels out, and in both cases you can minimise the aerodynamic impact of both. If we go back to some of the CFD images that we looked at earlier, you can see that we have large stagnation regions right on the front of the wheels, and I've just highlighted them now. The problem with wheels though is that they rotate, and by rotating they actually flick air everywhere, and I'm going to insert a little bit of a video now to try and demonstrate that. And as you can see from this video, the air is just completely chaotic, there's vortex generation everywhere, and it's just a complete mess. So really you want to try and minimise that effect as much as possible. The other thing that you'll notice on the CFD images now, and I'm hoping that you're starting to keep up with me, is that we actually have a little bit of separation here, and that's the blue region. The reason for that is actually to do with the coverings on this particular wheel and the fact that they bow outwards, a little bit like a triangle like that. That isn't great for airflow, and in fact you want them to be as flat as possible. So if you look at the picture of Dougal, their wheel coverings are flush with the side of the car, which means that the airflow is likely to stay attached all the way down. So if you are going to put wheel covers on your car, try to make them about the same width as the tyre and not to bow outwards. Now, if you are going to put your wheels on the outside, one of the things you can do is you can create a fairing that will try to control the air going around your wheel. In automotive, we do this by putting a front wheel deflector on, and that means that the air hits a flat, stationary surface rather than a rotating one. In this example here, Dylan has done this by putting fairings on the front. So the airflow hits the fairing, and instead of hitting that front rotating surface, it's now encouraged to go around the side like that and remain attached to the wheel. Similarly, it directs the airflow up and over the top. You can also see this sort of fairing in wheels that are enclosed as well. And there's an example here on Firebird, where they're faired at the front and the rear. Again, this is to try and stop having a stagnation point on the tyre itself. So these are sort of ideas that you can look at doing if you want to put your wheels inside or outside. I hope that was useful and it gave you a bit more of an insight into the opportunities to improve the aerodynamics on a Greenpower car. And if you have already been doing some CFD, perhaps it explained a few things that you were seeing but you didn't quite understand. But otherwise, thank you very much for listening, and if you have any questions, just pop them in the comments below.